Hi, welcome to Ethereal Mechanics Behind the Scenes. I'm going to talk today about what's been causing the delays. One of the problems I have in producing these videos is the fact that my home with all my equipment is up in the mountains. It's my home. But I also have an apartment near my job. And these are 250 miles away. And most of my equipment and machinery and stuff is here. I have at the apartment the ability to do software and the ability to do PowerPoints. That's why most of my videos are PowerPoints. And so the experiments require me to have a lot more time here. What I'm running into is a problem with the weather. Right now there's a blizzard outside, and the reason why the videos are on a 2-week delay is because my job gives me a 3-day weekend every 2 weeks that I come up here to do the video production, and that's why the videos are on a 2-week cycle. And the problem we're running into in this February, we've got a lot more snow than we've ever had before. And when I come up to the house, like my first day and a half is just doing maintenance on the house, repairs, things I need to do to maintain the house. It gives me about a day to work on the video. And right now today we've got a snowstorm, and if I don't leave pretty soon I'm going to be stuck trying to get back to the apartment. So the snow is one of the problems. The other problem that's happening with the very, very cold weather is that it's causing a problem with my solar panels, which has to be fixed. The problem with it is normally what I have is my solar panels are in banks of 4 in series. Now in the normal summertime, that bank of 4 will produce 110 volts open circuit. And the reason why I do that is because the distance between my solar panel array and my solar charge controller is about 175 to 200 feet. And I'd rather send that power down as voltage rather than current, so I stacked my panels in series. There's actually 4 sets of these in parallel. But the problem I'm running into is in the really, really, really cold weather, these panels actually prorate such that they're producing above 140 volts, like 145 volts in the dead of winter. So at noon, on really, really cold winter days, this guy is giving me over voltage warnings. And he can be damaged if the voltage exceeds 140 volts. And so I've been trying to come up with a solution to this problem. This only happens in the winter. It's not like it happens year-round. And so one of the solutions is to put a diversion controller on it. And what's a diversion controller? Well, if I take the power coming in from the panels, which normally go to the solar charge controller, what I'm going to do is put a circuit using one of these these are modern power MOSFETs. They're very, very beautiful. As far as, if you won't consider silicon beautiful, they're beautiful. I'm going to put one of these, and it only needs one of these. These guys can dump 90 amps, and they can hold back 200 volts. And I've calculated from the existing set of panels. The new set I'm putting on, I'm going to have to double this, but let's just worry about getting the existing set protected. And then put a Zener configuration. That'll give me 136 volts of DC reference. Such that, and the turn on for this guy is about 2 volts. So that means as this voltage here goes above 138 volts, this guy's going to turn on. And he's going to start dumping the power. Anything above 138 volts, he's going to dump. And what I've chosen for him to dump it into is a hot water heating filament. Because these guys are 4.5 kilowatts, which makes them at 240 volts, which makes them about 19 ohms, I've calculated. And what I'm going to do is just test this on a bench top just by putting regular AC into this and seeing if it clips the tops of the AC peaks. And if that works, I'm going to go and buy maybe a small hot water heater, and in the basement just put this circuit in parallel. I'm going to put an Arduino on it to monitor it, monitor all the voltages, so I can take some data over time to see if there's a failure condition I missed. So I mean, there was another option of putting a circuit like this ahead of it to block the power from coming in. The problem with that is you run into a high probability of it oscillating and also because this guy is a dynamic load, that dynamic load may affect the stability of this guy, and then you might end up like hammering this guy with big current spikes if this thing oscillates. So, and I don't want to spend a lot of time developing this. I just want to put a simple circuit that I know is going to work very well at shaving the excess voltage off the top to protect this guy. So this is another thing that gets added on, because of this cold weather that we've never really had before. Right now, until this is done, I've got to disconnect the solar panels while I'm not here to protect the solar charge controller. So that's one of the things that gets piled on that was unexpected. So, what else is in the works here? Well, I finally also went through my transistor collection. What's left over is a pile of junk transistors. Most of these are junk because they're not marked, or they're not marked with normal transistor numbers. They're marked with house numbers. What's a house number? Well, in the old days when people used to build transistor circuits like televisions and radios and whatnot, they didn't want their competitors to open up their radio and reverse engineer their circuit. And so instead of buying transistors with the normal manufacturer part numbers on them, they went to the manufacturer and says, hey, could you give me 10,000 of these XYZ transistors, but put this special code on it. And the special codes were kept, at, like Zenith would have their own numbers, and everybody would have their own numbers, so that no one would know what the transistor actually, well, they could guess, they could probably get pretty close, they could probably go through the trouble of measuring it, okay, but they wouldn't know that the exact, specifications were. It would take them, maybe it'd be very difficult to match it to begin with. Okay, so that's why a lot of these are, like this TR25, I believe, is a house number that you can see there. The other problem with these is some of them are just plain junk. I mean, when you start looking at some of the specifications on this old silicon, especially the power train, most of the small signal stuff I just pulled right out because they're actually still usable, even though they're for the most part junk. I mean, not that I would use them, like these old germaniums, which are a surprise. I didn't know I have that many germanium in the collection. These are more of a curiosity than anything. And what I may do when Ethereal Mechanics is kind of, done and over with is pick one of these, go find a circuit that germanium transistors work better than anything else, and just do a video on designing a circuit using an old, just for what do you call it, for reliving glory days, or like going back to it's like when you get an old biplane and you go messing around with it just for fun of nostalgia. That's what it would be, nostalgia. I mean, and look at these ones here are old grown junction transistors. They were designed before we learned how to miniaturize stuff, like in the Apollo age, the early 60s. These are like 1957. The specifications on these are so bad, I can understand why people didn't automatically jump from tubes to transistors. And where we've come from this is so fantastic. I mean, this little transistor here, I'll get rid of this pile of junk here, and this just only represents about 10% of the transistors. The rest I pulled out because they could be used, or for whatever reason they're still somewhat usable. I'd probably not use them on a project that I'm going to give out. But I may use them for nostalgic reasons, or maybe because repair something. But we're going from these antiquated 1950s technology to the more modern transistors. This little guy here, the comparison is these germanium transistors. Many of them, especially these older ones, will burn out if you put more than a tenth of an amp through them, and the best they can hold back is like maybe 20 or 30 volts. So they're not very powerful as things go, and their gain isn't too bad. But this modern little transistor here, this one was purchased for the new inductance meter. This is one of the set I have. This little guy has a drain to source voltage of 30 volts, and it can dump 100 amps. I mean, this little guy can dump 100 amps. I mean, it's not at 30 volts. It can do it at like 1 or 2 volts, but essentially, what this thing is a voltage-controlled short circuit, because when I was trying to develop the inductance meter many years ago, I needed a way to short the output for calibration purposes. And the best I could come up with as a way to short the output was these guys here. These were actually purchased back then. I don't know if the newer ones aren't any much better. This is a Max 4665 analog switch, which has a 0.5 ohm on resistance. At that time, that was the best one I could find. But now with these new modern MOSFETs, this guy has an on resistance of 0.0009 ohms, less than a milliohm. This is essentially a voltage-controlled short circuit, which is remarkable. I mean, it's remarkable where we've come. These guys I showed you before, these guys can also dump 100 amps, but they can also hold back 200 volts. So they're more appropriate for a high voltage application, or higher voltage application. So it's just amazing where we've come with silicon these days. It's just incredible. I can go off on all the things that have changed over my 30 years of doing electronics. It's just amazing what's available today. So what's in the works? Well, like you said, I'm working on the Foundation series of videos. And what's happening here is I was going to do the introduction to the Foundation series videos first. But as I'm getting into the meat of the things to support the Foundation, I'm actually like every time I go back, things get better. I've come up with better ways to do the rules of acquisition, and I'm going to redo the version 3 of the rules of acquisition. 1 through 9 are going to get sorry, my speech is a little messed up. I've had dental work, and the temporary crowns that the guy put in are like broken glass against my tongue. It's hard to talk. Sorry about that. But the version 3 of the rules of acquisition are coming along fantastically. 1 through 9, rules of acquisition 1 through 9 are going to be revised. Some are going to be outright replaced because they're really of no use. They were more for fun than they were utilitarian. But the new ones are going to be all utilitarian. Because, I mean, what happened was as I developed the rules of acquisition, the first few were kind of more like fun, and then they started getting really, really good and really, really detailed and useful as I went on. Well, the first 9 have to be reissued so they have that same utility that the later ones had. And also what's going to be one of the new rules is the smarter monkey theorem and science is anarchy. A very interesting video that a lot of people don't realize, that there's no regulating body in science. But we'll cover that when we get to the rules of acquisition. Then there's the Distinti gateway feedback theory, which was improved because of Q algebra. I learned a new way that we actually do science that didn't really dawn on me until I did the Q algebra. We're going to get into that. So Distinti gateway feedback is going to be its own video. And then the experiment videos. Each experiment's going to have 3 videos: a theory video, a demonstration video, and a how-to video. And these are some of the videos. Some are experiments, some are software simulations. The very last one, which I don't have a number yet because I think there's other ones in here that I forgot to write down, is the inertial field demonstration video, where we're actually going to move charge using an inertial field. And I'm going to show you that you cannot explain that with classical electromagnetic theory. And working up to this, I have to build a high voltage power supply, a decent one. The one that I purchased is very clunky and it's not very reliable. So and all of these things require a lot of software. So a lot of software is being done in the background. So there's a lot of work I got to do on this stuff. And the reason why I'm doing all this stuff first, and hopefully I'm shooting to get the introduction videos, probably 3 videos, to the Foundation series done last, is because trying to do these first is problematic. If I do all this background work first, then I can lace them together really nicely in a video and put all the links to all the Foundation videos. And also, because I'm going back and redoing these, I'm finding better ways to say things, cleverer ways to demonstrate things. And so to be able to put those clever stuff in the introduction video and lace everything together nicely is going to work out much better. So that's why I'm reversing the order. We're going to do these. The dual loop experiments coming up next, along with some of the rules of acquisition. I think 1 through 3 are in the pipeline next. And then I have to get software done before the rhombus experiment. I'm going to release the software needed to do the analysis. And obviously these are all software simulations here. And this Paradox 2, I want to rebuild it so it works a lot better than it did before. So what I'm looking for is to get this done before July 3rd. I've got 2 weeks off in July. And I'm hoping to cap off my July vacation with getting this Foundation series done. So, I mean, bear with me. There's a lot of work I'm doing all by myself. I don't mind. I'm having loads of fun now that I don't have to worry about that other thing I used to have to worry about. So I don't mind. Now, there's one thing that, you know, when I drive back and forth from my home to my apartment, I'm finding that if I do audio books, it helps pass the time. Dean Koontz is an excellent audiobook author because I end up not getting distracted. I end up getting really engrossed, and the trip goes really nicely. But in this one here, The Moonlit Mind, he has a very interesting dialogue at the very end, and it goes like this. The true nature of the world is veiled. If you shine a bright light on it, you can't expose that truth. It melts away with the shadows with which it was cloaked. The truth is too awesome for us to stare out directly, and we are meant only to glimpse it from the periphery of our vision. If the landscape of your mind is too dark with fear or anger or doubt, you are blind to all truth. But if your mental landscape is too bright with certitude or arrogance, you are snowblind, and likewise unable to see what lies before you. Only the moonlit mind allows wonder, and it is in the thralls of wonder that you can see the intricate weave of the world of which you are but one thread, one fantastic and essential thread. So I will leave that with you today. I thank you for your patience and realizing that I've got a lot of work to do to get these videos done, because experiment videos are a lot more complicated and I don't have as much time here at my facility to get the videos done. I mean, to get the experiments done, but they will get done. So thank you for your patience.